the present. Okay, and we have the last presentation. We present Ivana Wasowicz. The title of the presentation is Crack Growth Analysis and Residual Life Estimation of Structural Elements under Mixed Modes.
My name is Ivana Wasowicz. I'm coming from Institute Lola from Belgrade, and I will present you our work, Crack Growth Analysis and Residual Life Estimations of Structural Elements under Mixed Modes. Subject of this work is fatigue crack growth analysis using the different model, Paris law and strain energy density method for analyze the crack growth, and numerical simulation for a determination of stress intensity factors for two mode 1 and mode 2. We calculated the equivalent stress intensity factor in mixed modes and the angle of crack length for each increment of crack length. And here are two types of problems considered in this work: determination of crack growth trajectory and residual life estimations along the curved mixed mode. For this purpose, we used software package Nastran to determine the stress intensity factor. Here on this slide is present acquisition for Paris load. This is conventional load for analysis of fatigue crack growth. Here we use the dynamic characteristics of materials, that is C and then Paris constants. We determine them using the experimental methods, and then we know this fatigue crack growth rate. And maybe the little bit better method is strain energy density method, because this method using the low cycle characteristics of materials. That characteristics we get them from the experimental testing for the crack initialization, and the same characteristics for the crack growth. So we can use that characteristics determine one time. For determination of the crack growth trajectory, we need to determine this angle theta, what angle of each increment of the crack length. We get first length for the initial crack length, and then for each increment of that crack length, the new angle of that length, and then to calculate the equivalent stress intensity factor using stress intensity factor for mode 1 and for mode 2, and that angle we calculate from these equations, depending of the stress intensity factor for two mode, is it positive or negative value. Here on this slide we can see the geometry of specimen for modeling of crack growth trajectory with initial crack. Like I already mentioned, here we have two types of problems: determination crack growth trajectory and residual life estimation along curve. And to determine this stress intensity factor, we use Nastran software package. This is how it looks from the Nastran stress distribution of crack specimen using finite elements. For this purpose, we use the load in epsilon direction of 600 newtons, and the competition crack growth trajectory for the new increment, for the new increment of crack length. And you can see here how it looks, the stress distribution of the specimen and on the end of the crack. To validate this computational method, we used we use the experimental testing. For experimental testing, we use the servo-hydraulic MTS system. It's on this figure, and we introduce the load in this specimen, and then we determine the crack length in experimental. This is the detailed view. After that, we need to compare these results. We get using finite element method and using experimental testing. Like you can see on these two diagrams, we have a very good agreement between this result of experiment and using the finite element method. For residual life estimation, to determine computational residual life, here is used Paris law and the strain energy density method. For analytical formula for equivalent stress intensity factor, we used this stress intensity factor for one mode and two. For determination analytical formula, here is used discrete values of stress intensity factors, and discrete values are of the finite element method are given in next table. That's here for the different crack length. We have values of the stress intensity factor 1 and 2, and for angle theta. And then this is expression for calculating the equivalent stress intensity factor, and how to obtain analytical formula for stress intensity factor along the Craig-Grove trajectory. This is a formula we can use for every new case, because we have no in literature we have no any expression for this. So using these methods we can obtain this formula for future. This is Paris constant we get from for the experiment, and for this considered steel, this high quality steel, and load we introduced in the specimen. We used the load of maximum stress of 250 megapascals and the minimum of 25 megapascals. Crack length and then we analyze crack propagation for this load. Crack between two holes, like we had on the figure on previous slide, is compare these results of Paris method and experimental results, and comparing the results of strain energy density method, experimental method, and Paris law, we can see very good agreement of all these three methods, but maybe a little bit better agreement between strain energy density method and experimental testing. This is a practical application of this steel. This is a helicopter tail rotor blade of the two parts. One part is of composite material, and this another part is from that steel we test here in this work. That's CAD model of metal part of this helicopter blade, and then we have a stress analysis in metal part of this blade. For the conclusion, I can say that in this work, computational procedure to predict direction and the crack growth rate of mixed mode fatigue crack using mode 1 and mode 2 data from finite elements has been attempted. That we have very good agreement between these results we used from numerical simulation and results on experimental testing, and we can use these results we get here for every complex structure or part of the structures for that haven't be these aircraft structures or something like that. It's any mechanical structures this can be used for any mechanical structures. Authors would like to thank the Ministry of Education and Science of Serbia for the financial support of this work, and thank you for your attention.